This chart shows the time taken for different CPUs to transcode the same file from MPEG-2 format to QuickTime H.264 format, and it is updated on a regular basis, so it may not be identical to the CPU chart that is on Cerise.com. The first thing to note is that as you go up the graph, you can see that the greater the number of cores or processors available, the faster a video file will render or transcode, because rendering or transcoding is a highly multi-threaded process where the number of cores available is more important than the frequency at which they operate. We can see this most clearly with the CPUs on bars 2 and 3. Intel introduced these two new 6-core CPUs in mid-November 2011. They are the i7-3960X and the i7-3930K. They are the fastest single-socket CPUs available today. They are the first 6-core CPUs to use Intel's latest CPU architecture, which is Sandy Bridge. Previous 6-core CPUs used the Nehalem architecture, and you can see those CPUs here on bars 4 and 5. You can see that the latest Sandy Bridge 6-core CPUs on bars 2 and 3 are about 15% faster than the Nehalem 6-core CPUs on bars 4 and 5, even though the frequency and number of cores are the same. So this just shows just how far we have progressed from the Nehalem to the Sandy Bridge architecture. The other point to note here is that even though the 12-core system on bar 1 is a Nehalem architecture CPU, which is an older and slower architecture than the two new Sandy Bridge architecture CPUs on bars 2 and 3 here, the 12-core system here is still around 12% faster than the CPUs on bars 2 and 3. Because although it is operating at a slower frequency than the two 6-core CPUs here, in highly multi-threaded tasks like video transcoding and rendering, cores are more important than speed. In other words, I need those cores to process the file being rendered or transcoded much more than the speed at which this process takes place. To emphasize this point, you can see that there is no difference between these two new CPUs on bars 2 and 3 here in transcoding time, even though the CPU on bar 2 is 100 MHz faster than the CPU on bar 3, because again, for highly multi-threaded applications, cores are more important than speed, and the 100 MHz difference in speed is not going to make much of a difference in a highly multi-threaded application like rendering. Now, for applications that are not highly multi-threaded, like for example Photoshop, speed is more important than cores, and although I do not show it in this chart, the CPU on bar 2 is about 5 to 10% faster in Photoshop than the CPU on bar 3, because the CPU on bar 2 has a frequency which is 100 MHz higher. To find out why CPU architecture makes a difference, take a look at episode 5.